Well, welcome everybody to the March meeting of the Amateur Astronomers Association of Princeton. And we have an exciting night for us in store. I have a few things, announcements and the like to talk about, and then we'll get into our main theme with our guest speaker tonight. After which we'll take a brief break and pause the recording and so forth. And we'll ask you guys to come back because we got quite a few things to discuss astronomy by and for members. So my name is Rex Parker. I'm the director of this fierce group. We, of course, are continuing now. We've been a full 2 years away from our home, Peyton Hall, the Hall of Astrophysical Sciences at Princeton University, and we miss it dearly. Really nothing to report to you except to say we've got our finger on the pulse of things with the university, and we're hopeful that things could change, but clearly they will not be changing this year. We've got a few meetings to go. We'll continue Zoom for the next 2 months. And then the June meeting, actually, we will have a bit of a bold initiative. We are going to return to the planetarium at the State Museum in downtown Trenton, where one of our esteemed members, Bill Murray, is on the staff, and he will guide us through a night show there, kind of reprising what we have done in the past and acting like we're normal again. So maybe that will be a good omen for the future. And then after our summer break, we can talk about where we're going to go. I do have a little bit of information about what's happening at our observatory in the Washington Crossing State Park. We, of course, are getting ready to begin a new season, which traditionally our public outreach programs, as well as our regular member access to the observatory and our telescopes out there, are beginning their season in April, weather permitting, of course. And we're going to talk after the break in more detail about what's happening there. There's plans underfoot to get the key holder groups organized, and Dave and Jen are working on that. So we'll come back to that. But what I wanted to convey to you was the question that I put to the state park and the DEP. The New Jersey DEP is the overlord of the state park system, and we take our lease from the state park. So ultimately, they are the ones who set the public policy for our observatory operations. And so, as you know, we've been operating on COVID rules for the last year and a half, 2 years, and we've basically been more of a plan B or a level 2, if you will, of the COVID rules, where we do have access and we can have public out there, but we have to maintain some bit of social distancing. And without getting into those details, I'll say that I got an email response back today from the superintendent at Washington Crossing Park, Neil Ferrari. And I'm just going to read his reply just so everybody hears it straight from the horse's mouth. He says, "At this time, I have no new information regarding any changes to COVID protocols for public events. Barring another surge in cases, it seems reasonable to assume there will be some change forthcoming, but I am not currently in a position to predict what those changes will be or when they will be implemented. Therefore, you, the AAAP, should continue to operate in the same manner as you were last year until we receive new guidance. Sincerely, Neil." And that guidance may well come from the form of a governor pronouncement. I think we're waiting to hear some things from the top level in New Jersey, and it'll filter its way through. I do expect some things to change. And so let's just say our plan will be to continue with our somewhat conservative protocols, social distancing, limiting the number of people on the site. But on the other hand, you can get out there, coordinate it with Dave and the others, and we'll continue to play by those rules until maybe the near future and the ice finally breaks. So that's that. I just want to mention a couple of other things. The observatory is getting back into shape after the season off. And one of the things that happened that I'm sure Dave's going to describe in more detail later, but we had an issue wherein, without getting into all the gory details, we need to place some new carpet down on the floor inside the observatory. And so the question has to come up, what's the best way to furnish a concrete floor of a permanent observatory, very roughly 24 by 12, 13 feet in dimensions. And we want to pay a professional carpet installer to give us a nice new carpet out there. And so the reason I'm bringing this up is we're seeking a member who may have experience, or maybe your spouse has experience, your household. I certainly have zero experience in this department. We'd love it if a member could step up and just basically be the liaison between the club and some carpet installation firm and get the ball rolling, get a quote, and get something going there. If you feel like you can contribute, that'd be such a big help to the club. Let's talk about it after the break. So just tossing that out there for you. Also tossing out there, I set up a little Zoom poll, which we will also do after the break. It'll come up on your Zoom screen. And I'm going to ask you to answer a handful of questions that are concerning outreach and some other aspects of our club activities coming up. So please help us get the information we need by taking the Zoom poll. It is anonymous, so nobody's going to get incriminated by saying the wrong thing. No, actually, it's just fill in the blank, so you can't see anything wrong. One other thing I wanted to mention is we are encouraging our members to get involved in something called the Night Sky Network, which is an offering that has been put together by NASA and the JPL at Caltech, together with the Astronomical Society of the Pacific. And they put together this very nice web cluster of capabilities and content. And our club has been now for a couple of years an affiliate member of the Night Sky Network. And there's a lot of good that can come out of being involved with this. And I won't get into that right now, but I'm going to ask you guys, if you have not yet, to register in the Night Sky Network as a member of AAAP. And I just sent an email earlier tonight to all members, and it has a link to and instructions on how to register and some other information about the benefits to be gained. So we're asking you to do this. And again, we can come back after the break and talk more. Why are we pushing yet another social contact thing out to members? We did the Discord app with our AAAP channel, and that's been working out very well. And we have nearly 100 members who have signed up. But I mean, fairly obviously, with the limitations that COVID is giving us, we're seeking ways for members to get in touch and to be able to communicate with each other. And this is another superb way to do that, as well as gain access to some really, really cool things that are coming out of none other than NASA and JPL. So enough said there. Check your email tonight. I sent an email to all members. All right, well, no preamble to our meetings would be complete with a little bit of what's up in the sky. And we do like to do astronomy in this club as well as talk about it. And there's some really good opportunities coming up, whether it's out at the observatory or whether it's you in your own backyard. We've been doing some sessions this winter. About 20, 25 members each time have joined our Astro Video live sessions, where we've literally taken our backyard telescopes and linked the output of our video CMOS cameras right into the Zoom meeting. And that has worked out superbly. And it's something we want to find a way to continue as we get away from the winter and more into the warm weather season, how we might continue that in the future. It's something else we can talk about. But right now, I'll just draw your attention to the star chart here for 10:30 p.m. tonight. Looking right down the center line there is the meridian. And notice how the constellations, I don't know if you can see my cursor, the winter constellations, Orion, our favorite with the incredible objects in the belt of Orion, is now moving to the west, and soon will no longer be a midnight sky object at all, but rather spring season is galaxy season, and all these blue marked Messier objects are coming into prime view. And these will be the subject of what we're going to be attempting to look at out of the observatory and elsewhere in the coming months. And I'll just draw your attention to a couple of them here. The cluster down by Leo and Virgo and Coma Berenices on a more and large scale here, it's truly astonishing to realize the density, if you will, the number of these galaxies. And what I've plotted here are brighter than magnitude 12, which is absolutely mind-blowing when you take a telescope. Even in our light polluted skies here in central New Jersey, you can pick out numerous of these objects. And I'll just mention, because I was sort of catching up with my Sky and Tell issues, this afternoon. There's this really great article in the March, I think it is, Sky and Telescope about how William Herschel, when he was first creating the objects that became the centerpiece of what's today the NGC catalog, how he actually went about observing. And one particular night was highlighted in this article in the Sky and Tel March issue, where he and his sister Caroline logged in some incredible number of these objects right in this zone near Coma Berenices on one particular night, April 11, 1784, speaking of history of astronomy. So check out that article. It's very cool. And you realize, this is the sky is dripping with human history as well as incredible celestial information. So I'm just going to highlight a couple more. At our recent Astro Video live session, we had 3 telescopes going, and the objects that I've circled here in yellow, we brought right up on the screen live with our video cameras and our telescopes, and they were pretty astonishing views. And just to share with you, I have these from my own work. Okay, admittedly, this was not the live view. This was more of an extended multi-hours image, but this is from my backyard here in the Princeton area, Messier 51, which, I don't know, maybe our speaker tonight has a special affinity for this particular galaxy. It's amazing to me how our equipment can bring these things up despite what we're facing. Messier 97, the Owl Nebula, the Owl Nebula, which is a planetary nebula, the remnants of a star that's gone through some big changes in its life cycle. These are all quite visible in the live screen from our EAA, if you will, our Astro Video live sessions. And some of my favorites here in Leo, Messier 66 and 5, and they're close enough together. Even with my big telescope, I can fit them into the same field of view. So this is a single image of these 2 guys. So anyway, you gotta love the possibilities. We can talk more about that as we go into the second half of the meeting.
I want to welcome our guest speaker for tonight, Dr. Rosanne Di Stefano, who's Senior Astrophysicist at the Center for Astrophysics, Harvard and Smithsonian. Her talk tonight is about exoplanets in distant galaxies. Almost all of the nearly 5,000 exoplanets discovered to date are within 3,000 light years of Earth, or they were. Dr. Di Stefano and her colleagues may have discovered an exoplanet transiting a star in M51, the Whirlpool Galaxy, about 28 million light years away. They did this by examining light curves from 238 X-ray binary systems in the galaxies M51, M101, and M104. One exoplanet candidate turned up, now known as M51 ULS1. Because the region glowing in X-rays is comparatively small, a transiting planet could block most or all of its X-ray emission, making it easier to spot. Dr. Di Stefano will describe her research and its implications for planetary studies, including possible extensions of this work to X-ray binaries in additional galaxies and in the Milky Way. A few words of introduction about our guest speaker. Dr. Di Stefano is a graduate of Queens College, CUNY, Columbia University, and SUNY Stony Brook. She's a senior astrophysicist at the Harvard-Smithsonian Center for Astrophysics. Her thesis work was on Hamiltonian dynamics and supersymmetry, and she's been looking to answer questions in astronomy since the 1990s, first at MIT, then at Harvard, and at the Smithsonian Astrophysical Observatory. Her current research interests are binaries and triple star systems, particularly topics related to the progenitors of type 1a supernovae, gravitational mergers, and binary self-lensing. She works with both newly collected and archival X-ray data and is engaged in time series analysis for both X-ray and optical events, including microlensing. Dr. Di Stefano is a member of the Vera Rubin Observatory's team on transients. She's active in science education and outreach and in community service in the US and abroad.
So here is an image that we were just looking at a few minutes ago with a slightly different orientation. This is the Whirlpool Galaxy M51. And on one side, you're seeing the optical image, and that's very familiar. Of course, you see the light from many different stellar systems, and you also see gas and dust where new stars are being formed. On the left, you see the X-ray image. And these point sources are really mostly X-ray binaries, individual systems where two stars orbit each other and X-rays are generated, as we'll discuss in a little while. A big contrast between these images is that when you see what looks like a point source in the optical, that is very likely a large star forming region or a cluster of stars. When you see a point source here in the X-ray, that is one system. So in some sense, these X-ray sources that we're going to be talking about today, I like to think of them as the Einsteins or the Shakespeares of their galaxy, because they stand as around 100 some odd systems out of more than 100 billion stars that live in the galaxy as a whole. And here in optical, we see the blended light from all of those stars, whereas in the X-ray, we can actually pick out some individual systems and study them as individuals. So that's just a kind of a prelude that will come up again later on in the talk. Now, we have been thrilled with this result about being able to extend planet searches to such large distances to other galaxies. And this is the team of people who did the work. I want to point out Julia Bernson, who is now, she started this as a high school student. She was just entering her senior year of high school. She's now a sophomore where you are at Princeton. And this is the rest of the team. Some of their names will come up as we go through the talk. So an overview of what we'll discuss tonight is we'll touch on external galaxies, X-ray binaries, which are the systems you saw in the image just now, and how would you find a planet orbiting an X-ray binary? Let me go back to this picture. Nia Amara, who is here, Nia and I worked together on this, and it's the work that we did together that she led that led to the project I'm going to tell you about now. So once you know you can find a planet, you actually have to search for it, and that's what this project is that I'm telling you about. And I'll tell you about the candidate planet that we did find, and we can also discuss together some possible next steps in the field. So the Milky Way itself, which we saw in the night sky today, right? The Milky Way has been an ancient puzzle. And for as long as there have been people to look up at the sky, they have seen stars, and they have also seen this band that looks like a cloud cross the sky, the Milky Way. And the question through the ages, likely for more than 1 million years, is what is this? So in 1610, when Galileo turned a telescope that was good enough to do astronomical observations to the sky, he had the answer to this age-old question. He saw that the Milky Way resolved into stars, that it is not a continuous cloud, but that it is made up of stars. And what he said about the sky is, to whatever region you direct your spyglass, an immense number of stars offer themselves to view, of which many appear very large, but the multitude of small ones is truly unfathomable. Right? So this was the sky that Galileo could see. He could see stars that we now know are part of our Milky Way. He could see the Milky Way itself and resolve it into stars. And it wasn't too long thereafter that one of the things that people who study the sky began looking at are dim nebulae, dim clouds that are scattered across the sky, many of them out of the plane of the Milky Way. And this is a very low resolution image of the very galaxy and its companion that we have been talking about. This is M51. So what are these nebulae? That was an open question. And this discussion continued right up until 1929. But by the mid 1750s, so by the mid 18th century, people were already beginning to conjecture that these could be island universes, that they could be analogs to our own Milky Way galaxy, but they look as small as they do and as dim as they do, simply because they're very far from us. And, these are now almost unimaginable distances, right? Compared to the distances between us and the nearest stars. Now, human beings, this is one of the things we do, right? We see something that we know and we see something that we don't know, and we ask ourselves whether that thing that we don't know could be like the thing that we know. So this is what the philosophers and natural scientists in the mid 1700s were doing. And we've done this even earlier when people looked at stars and realized that stars have natures similar to that of the sun. If the sun has planets, maybe other stars have planets as well. And so this was the question: do other stars host planets? Now, the sun is not a very exceptional star. If it hosts planets, then perhaps other stars do as well. This is also a question of longstanding, not as longstanding as what was the Milky Way, but also a question of longstanding, and people tried to answer it, but we just simply didn't have the technology, because stars are bright and planets are dim. They're shining by light reflected from the stars. They're close in distance. When we look up at the sky, the planet is not resolvable from the star in most cases. Today, we can actually separate out the images, but that wasn't possible until fairly recently. And so finding planets was a great technical feat. And these technological advances that were needed started to come into fruition around the late 1980s. And the first recognized, confirmed discovery was actually a very unusual planetary system, not one that people were expecting to find. So this was a planetary system, at first just one planet discovered, orbiting the remnant of a massive star. So the remnant is the neutron star, about 1.4 times the mass of the sun, but compacted into a region that is roughly the size of Manhattan. And this star is spinning. This particular one is spinning almost 1,000 times per second. And because it is spinning so quickly and it is so massive, it is a wonderful clock. And using the timing properties, we were able to discover a planet orbiting this object. So I think most people were probably hoping that we would find planets like Earth orbiting a star like the sun, but this was for most people a surprise. And fortunately, it was happening at a time where it did become possible to find planets in other ways. But let me tell you a little bit more about planets around pulsars. The image I'm showing you now is an image of a globular cluster. You're not seeing the whole cluster. If we were, farther away from it, not looking at it so intimately, you would see what appears to be a globule of stars. We're looking at one part of it, and this green circle marks the position of a system that I'll show you now. At least this is the artist's conception of that system. So here is a millisecond pulsar, and you can see it by the jet here. That was the way the artist is telling us. That's a millisecond pulsar. It has a companion. This companion is a white dwarf. A white dwarf is the remnant of a star like the sun. Now, what we think happened is that today's white dwarf was once a star, possibly around as massive as our sun, and it was somehow captured by the neutron star. And at some point, as it started to go through the end of its own life cycle, it started giving mass to the neutron star. We often say that it donated mass. In fact, of course, the mass is being pulled off by the neutron star. And as it's pulled off, some of it gets to stay with the neutron star, although some of it may be also thrown off. The part that stays on brings with it angular momentum that spins the pulsar up. Well, oh gosh, I'm being offered an update. I hope that didn't disturb your view. So the neutron star gets spun up, and that's why it's at spinning at millisecond periods. When a pulsar is just born, it usually is spinning maybe around once a second or so. Now, the interesting thing here, you see this is the system that's massive and clearly had an interesting history. But the artist's image is dominated by this huge object, which is a Jupiter-class planet. I believe it's about 5 times as massive as Jupiter. And it's about 23 times farther from this system as the distance we are from the sun. That is about 23 AU. And this planet, we believe, was orbiting the system while the system was changing, while the white dwarf was having mass pulled off of it. That mass was falling on to the neutron star. As it fell onto the neutron star, a tremendous amount of kinetic energy was generated, and we had a great deal of heat, and we had X-rays generated. And so this system was an X-ray binary, and the X-ray binary was orbited by a planet. So although we don't see it today as an X-ray binary, this system gives us the idea that there is such a thing as planets orbiting X-ray binaries. And we just hadn't found them yet. So let's say a few words about X-ray binaries. You don't have to have a neutron star being the compact object that pulls mass from the companion. It could be a black hole, for example. And the companion is donating the mass. The mass is being torn away from it, traveling toward this compact object. It can't fall directly toward it, and so it falls toward it through a disk. And this disk is the so-called accretion disk, and the X-rays are generated from this central region closer to the black hole or to the neutron star. How many types of X-ray binaries are there? Well, it's a little hard to count them because you could have a neutron star or a black hole. You could have a donor star that's massive or low mass. It could be a giant star or not a giant star. It could be sending mass through winds, or maybe sending mass in this very controlled way through a neck in what we call the Roche lobe. Many, many different ways for there to be X-ray binaries. But one thing I do want you to notice is that there are irregularities in the flow of matter. Now, this is just an artist's conception, and I'm sure the artist didn't have in mind that I'd be showing the slide in this way. But even in this artist's conception, you can see that there very likely are irregularities. The thing to remember is that X-ray binaries are incredible environments. They're very unique. They're energetic. This matter that's coming in is ionized. It's a plasma. It's falling in. Tremendous amounts of energy are accumulating as the matter falls. It's a highly energetic, very likely turbulent system. And so it's natural that there might be irregularities in that accretion flow. And if an irregularity, such as a cloud, passes in front of the X-ray source, so imagine the X-ray source being toward the center here, and a cloud passing in front of it, you'll see a dip in the amount of X-rays that you receive. But because this object passing in front of the X-ray source is diffuse, so there's, it doesn't have a surface the way a planet would, or the way a star does. Star has an atmosphere, the Earth has an atmosphere, but it's a pretty well-defined region when you transition from being outside to inside. With a gas cloud, it's much more diffuse. And the matter interacts with X-rays as the matter moves in front of the X-ray source. And as the X-rays start interacting with that matter, they impart energy to it, and their spectrum changes. So we see, as you have a dip, which is what you're seeing down here, there's a change in the upper panel. The upper panel is labeled hardness ratio, and that's not an important thing for you to know about tonight. What is important is for you to know that when we see changes here, what we're seeing is we're seeing changes in the energy of the X-rays that reach us. So this is a kind of a proxy for the spectrum. And so as the gas cloud goes in front of the X-ray source, we not only have a dip, and that dip generally has a lot of structure, but we also have a change in the spectrum of the X-ray source. So these two things go together when it's a cloud passing in front of the X-ray source. Now, this is the point that Victor mentioned when he started his introduction. He mentioned that if you looked at the size of the X-ray emitting region, it's very small. It can be as small as or smaller than a planet. And this was the crucial observation that Nia and I made in 2018, where we looked at the probability, not only the fact that that's small, but that there's a fairly significant probability that we could see when a planet passes in front of an X-ray source, we could see the dip, the transit. And it wouldn't be like the transit of a gas cloud. It would be like the transit of something that has a well-defined surface. And these are just some images. Let's pay particular attention to this. This, again, is an artist's conception, but it's an artist's conception of a real system discovered by one of our former graduate students and a friend, Andrew Vanderberg, who found the white dwarf, a white dwarf that is orbited by a planet, a giant planet. And you can see from this, although it's an artist's conception, the fact that the dimensions of the white dwarf are smaller than the dimensions of the planet, that's true, that's real. So if you were looking at the white dwarf and the white dwarf happened to be emitting X-rays, those X-rays would be blocked when the planet passes in front of it. Now, this is not a case where the X-rays are being emitted, but there are lots of X-ray binaries that also have white dwarfs at the center. And they can emit X-rays, and they can be blocked by the transit of a planet. So this is what we're talking about geometrically. I'm showing you a special system. I'm showing you the system that we discovered, just by way of introduction. We have in here, you see that tiny red dot that corresponds to a compact object. We don't know if it's a neutron star or a black hole. And in this case, the star that is donating mass, well, it's always going to be bigger than the compact object, but in this case, it's a blue supergiant. So the fact that it's that it is a blue supergiant tells us that because it's blue, it's hotter than a star like Betelgeuse, and it's smaller. It's probably about 20 or 30 solar radii. And the companion was found by looking at this region with the Hubble Space Telescope. And I'll tell you that the planet that we found is orbiting in a very wide orbit, probably something like 15 AU from this central object. So in other words, it's 10 or more astronomical units from the central object. And you can imagine this tiny planet candidate orbiting the system. And although it's very tiny, remember that the other thing that's tiny is the compact object. So if we're down here someplace and we're looking, when that tiny planet passes in front of the tiny X-ray source, we will not see X-rays. And this is an animation that was made by the public relations team of the Chandra X-ray Observatory that, whoops, I don't know what happened to that. Let's go back. And it sort of shows what's happening. That big thing on the right is the star. The planet is coming in front of the X-ray source from our perspective. I'll show it to you again so that you can see it. It's a very brief passage in front of the X-ray source. There you go. Now I'm sort of giving away my bottom line. We didn't know this for a long time when we were doing the research, but I'd like you to be able to really visualize the system, which is why I'm sort of, giving you the punchline a little bit early so that you'll come away, with a reinforced idea of what this system is like. So it's a supergiant, blue supergiant, very small object, neutron star or black hole with an accretion disk, and the planet just passes in front of it from our perspective, covering the X-ray source. The event takes about 3 hours. So discovering this opened up a whole new field of exploration. And for this, all we had to do was to use data that already existed from the Chandra X-ray Observatory. And to do it, we really, the key was, first of all, being able to do a thorough search of the data, but also being able to do a thorough analysis of the data so that we could verify that we were seeing what it seemed like we were seeing. That's where all the hard work was in really trying to understand what we saw. So we were looking for the needle in the haystack. Some of you may be familiar with microlensing, where you have an object that passes in front of a distant object, and the gravitational influence of the foreground object bends light in such a way that we temporarily receive more light from the background object. And I'm showing you this particular picture because this was discovered by an amateur astronomer in Japan. This is called the Tego Event. The discoverer was Tego. He was an amateur who specialized in finding novae. He was out on, I think it was Halloween night. I don't know if that meant anything in Japan, but I believe it was Halloween night of 2007. And he found what was increasing in brightness as a nova would, but in a way that was unfamiliar to him, not nova-like. So he let people know about it. They followed it up, and they discovered that this is a highly unusual microlensing event. Most microlensing is found when we look at the central part of our galaxy where there are lots of stars, so that there's a pretty good chance that one star in the foreground will pass in front of one of these background stars. Tego was just looking at an arbitrary part of the sky. And he was looking at a bright star that's only about a kiloparsec away from us, so a few thousand light years. And he saw this remarkable brightening. His colleagues, who were the professionals who looked at this, were able to recognize that this is a microlensing event from its shape. And they also found that the spectrum of the star that was being lensed did not change at all during the event. This is one of Einstein's predictions for gravitational lensing. So we're seeing a situation where we can recognize the event by its shape and by the fact that the spectrum doesn't change during the event. And that's exactly what we're looking for when we look for the transit of an X-ray source by a planet. We can recognize the transit by its shape, and we recognize that it's not a cloud of gas and dust because there's no spectral change. Now, let me just see how we're doing for time here. I'll spend a minute or two on this, which brings us right back to where we started. So these are the individual X-ray sources that can be seen in a single image with the Chandra X-ray Observatory. And since the Chandra X-ray Observatory has imaged this region more than 10 times, we have lots of information about how each source changes in time. And that's why we can look for planets around individual sources. We can look for evidence of transits. We cannot do that at optical wavelengths. Many of you may know that in astronomy, there's the decadal survey that was just completed a few months ago. And the decadal survey is run by the National Academy of Sciences. And they're trying to look ahead to see what's the most important astronomy to do in the next decade. Now, I have not verified this, but it has to be the case that looking for planets in an external galaxy was not something that was in the cards as far as the decadal survey was concerned, because the methods that astronomers use to find planets in our own galaxy involve studying optical light or sometimes radio waves from things like pulsars. And you just couldn't separate one system from another in this very dense environment of the galaxy. It's only at X-ray wavelengths that it can be done. And in some sense, this is almost, I wouldn't call it an accidental discovery because we had to work very hard to do it. We planned to do it, but the fact that it could be done was not something that we knew long ahead of time. We discovered that it could be done and we followed up on it, but this was not something that I think was anticipated. So that made it particularly exciting. And so what we did is we studied these three galaxies, the whirlpool, the pinwheel, and the sombrero. And there were roughly 200 sources. They had each been observed multiple times. So we had about 2,600 different patterns of following the light as a function of time. That is about 2,600 light curves. And this is what the light curves look like. This is so-called sparklines. And what we did is we studied all the bright X-ray sources that had been observed for more than about an hour and a half. And we just simply said that we needed to have the counts in a 1,000-second bin of time go down to 0, and that there had to be a baseline from which the counts fell and to which the counts returned. So we applied it to all 2,600 light curves and we found one. And that's the one right there, highlighted in pink. This happens to be a highly luminous X-ray source, about 1 million times more luminous in X-rays than the sun is in all wavelengths. It doesn't emit hard X-rays. It emits X-rays that are more toward the lower energy bands, so just where we begin to call them X-rays. So we call this a soft X-ray source. And from the spectrum and luminosity of this soft X-ray source, we can derive an effective radius, which is a few times smaller than the radius of Jupiter. Okay. So when you're blocking it and you measure from the pattern of the blockage how big the transitor is, what we find out is that that also has a size that is not too different from Jupiter. Now I'm just showing you where this is in the galaxy. It's in a spiral arm. It's on the edge of a young cluster of stars. The blue supergiant counterpart is less than 20 million years old. So this is a very young system. And we had to ask ourselves, what causes that decline and the rise that we saw? And this is a picture of it. This shows a bit of a blow up of it. And this shows it in the context of the full light curve. So you can see it is a real fall, and that there is a region before and after where the count rate is about the same. Now, at first, when this was actually, we weren't even the first to discover this dip. It was actually first discovered by a couple of our colleagues, Ryan Urquhart and Roberto Soria, and some of their colleagues. But they didn't know about planet models for dips of X-ray sources. They did know about gas and dust. And so they guessed that it could be a dip due to gas and dust, but they and their colleagues were puzzled because it was unusual. It was different from all of the other such things that they saw. And when we started talking to them about the planet model, they became very enthusiastic that we should check it out and see if this is what it could be, because it could be a better explanation. So the first thing we did is to look at other X-ray dips. And here's an example of one. And I won't say much about this except to say this is a hardness ratio. And you can see that during the dip, the hardness ratio changes. That means the spectrum changes, and that's our clue that it's gas and dust that's passing in front of the X-ray source, causing the dip. This is our dip in M51 ULS1. And you can see that when we look at the hardness ratio, there is not a change. So this is distinctly different from the model where it's gas and dust. Could it be intrinsic variability? If so, it would be remarkable. We don't have a physical explanation for such a thing, because over 3 hours, it would mean that you had an object that dipped in luminosity to the extent that it would have to have changed its radius by a factor of 3. It would have had to shrink to 1/3 of its size without changing its temperature and then come back again in a symmetrical way. We don't have a physical model for that kind of variation. So let me just show you what we found. It's probably best seen in this graph, where we see the probability distribution for the radius of the transitor. So we looked at the shape of this transit, And a transit is just an object which has a circular cross section, having something pass in front of it that also has a circular cross section. So we can model this mathematically. And this is a calculation, the result of a calculation that shows us the probability that the radius of the eclipser has certain values. Well, this is, let me see if I have this right. I believe this is the radius of Saturn. Is that right? Yes, this is the radius of Saturn. And this is the peak of our probability distribution, the mode. So this tells us what the most likely radius of the transitor is. It is somewhat smaller than Saturn. It could be within the 90th, within 90% percentile. It could be as small as 2 Earth radii, or it could be as big as something like 2.7 Jupiter radii. Here you see the radii of planets that are Jupiter size, Jupiter mass roughly, but they're in close orbits with stars. They're called hot Jupiters. This is the distribution of their radii. This is the radius of a brown dwarf, an object which is not a planet and not a star, but somewhere in between. And the radii of young, low mass, small stars is on this side. So if you ask yourself what model fits the full range of radii, the first one that comes to mind is planets. The second one that comes to mind is white dwarfs. This could have been a white dwarf. But white dwarfs, because they come from stars like our sun, and stars like our sun live longer than very massive stars, we wouldn't have expected a white dwarf to be able to form during the lifetime of this system. But there's an even better reason why this couldn't be a white dwarf. If a white dwarf were in a wide orbit with this X-ray binary, it would not block light from the binary. The white dwarf is so dense and it has so much mass that it would actually serve as a gravitational lens, and we would get more light at X-ray wavelengths when it passed in front of the X-ray source, not less. So it's definitely not a white dwarf. Could it be a brown dwarf or maybe even a small star? Well, we can't rule that out entirely, but it's not very likely. First of all, at this age, this would be the very low probability end of our probability distribution. Secondly, young brown dwarfs tend to be bloated. Thirdly, this object, whatever it is in a radiation field of a very luminous X-ray binary, and is therefore perhaps even more likely to be bloated. Finally, brown dwarfs, at least the local brown dwarfs that we've been able to study, there are simply fewer of them than there are planets. So the most likely explanation is that this object, that is the transitor, was a planet. And the planet size is comparable to that of Saturn. And we call it, because it's in another galaxy, not an exoplanet, which is what we call planets in our galaxy that orbit other stars. So this one is called an extraplanet. And we can't say that it's actually a planet because we cannot rule out the explanations of brown dwarfs or very low mass stars. We can say that they're low probability, but we can't rule them out entirely. So this is a candidate planet. And what this demonstrates is that we have the ability to find planets in external galaxies. And this very likely is a planet, but it will always be called a candidate because we're not able to validate the model and tell you with 100% certainty that it is a planet. Now, we can talk a little bit more about confirming it later on. I want to bring this to an end just so that I, don't keep you for too long with this part of the talk. But I do want to say that this is a fascinating system. So this is whatever that orbiter is, and as I said, we think it's a planet, but whatever it is, this is a unique system. So this is an Xray binary with a very small object in orbit with it. And that small object is definitely not a compact object itself. So it must be something like a planet. That's the only thing that fits across the whole radius distribution. But what was this? And what is its future? It's fascinating to think about. In 20 million years, there's not enough time for life as we know it to have formed. So we think there's no chance at all that there's life associated with this planet. But we can look forward into the far future. Probably actually by today, the donor star has already finished its lifetime, and it may have already supernovaed. We don't know, because 20 million years or so, almost 30 million years that it took for the light to get to us from the time when the transit actually happened, that's enough time for the other star to evolve. So even today, if we could go there like that, which of course we can't, but if we could, and if we wanted to, which I don't think we really do want to go there, but if we did, we would find very likely that this system has finished its evolution. The planet may or may not have survived, in that it could have been ejected as the second star evolved, but it could also still be there. We need to study a little bit more what happens in this three-body dynamics when you have the end state of a star and a planet orbiting the system. That's a binary. If it stays there, it is a planet that now for the indefinite future will be orbiting two compact objects. These two compact objects could themselves start with, well, they are emitting gravitational radiation, but if they're close enough to each other, they'll emit enough gravitational radiation to merge within some billions of years. And then we have a planet orbiting a system that undergoes a gravitational merger. And we're really not sure exactly what that would be like. So this is a fascinating system. It has a fascinating past and a fascinating future in which the donor will fully evolve. And this planet could be close to the location of a gravitational merger. So I don't want to spend a long time on looking at the future. You may ask me a little bit about that, but I do want to emphasize something that I said before, which is that this search method is not one that has been used before. That is, to use the transit of an X-ray source. And so it has the ability to jump over other methods of looking for planets and therefore find them at farther distances. We can use this method also for planetary systems that orbit X-ray sources in the Milky Way. And that will be fascinating if we find some of those, because we'll have a lot more information about them than we do about any object in another galaxy. So I want to end by thanking all of the people who helped with this. These are the people who created some of our materials, and they did a wonderful job working with us as this work became public. we were talking about the Center for Astrophysics and the plate stacks. We also have a wonderful library, the John Walbach Library. And Maria McKeekern is one of our librarians who has been extremely helpful to me. Her husband, Stephen McInerney, happened to be reading a science fiction book drawn from the library, which is set in the year 2255. And that science fiction book predicts that we'll have the first glimpses of an extragalactic planet right around then. Well, I can't say that we've glimpsed this planet because we haven't, but we've seen its shadow. Okay. And that's a pretty remarkable thing for 2022. And again, I want to emphasize the wonderful work that was done by this team. I'm sure you know that today many planet discoveries are made by teams that include dozens of people. This was a small team with everybody bringing expertise from another field to be able to put it all together and do all of the testing and analysis that we had to do. And it was a pleasure to work with every single one of these people. So I just want to emphasize them one more time for you. And with that, I'll thank you for your time and attention. Thanks.
Wow, thank you very much. That's fascinating, absolutely fascinating. Let me open the floor for questions.
Victor, do you want to open the screen to the gallery?
Yeah,
Okay.
I'm doing that now, Rex.
Should I keep these up or should I, so that we can look at them again, or should I
Well,
try to do the gallery view so that I can see people?
Your choice. I would keep sharing your screen though, so if you want to go back to some of the
I can do
graphics.
that. I guess that has the one disadvantage that I may not be able to see the questioner, but that's.
Well, I think Ira's doing something about that now, right?
Oh,
Yes, yes, I make it so whoever's speaking is viewable. So that would box
Okay.
around.
Thank you. That's great. Okay.
Well, you know, I wanted to start by asking, you're talking a lot about, I mean, obviously these are X-ray observations, and I was curious about your choice of X-rays. I mean, obviously what you wanted was a source that was extremely luminous, so it could be seen at a long distance, but also very small, so that when the planet goes in front of it, it doesn't just do this minuscule little dip, it just
Right.
really announces itself big time. Are there other wavelengths or techniques that might accomplish that?
Well, that's really an excellent question. I really don't know of any right now, right? You have to think of two things. So one of them is just being able to do the discovery, which is what you're getting at by emphasizing the small size of the object that's being eclipsed,
Right.
the one that's sending us all the light, right, compared to the planet. So if you ask yourself, what has that kind of small size? The one thing that people have considered before are M dwarfs, very small dwarf stars. In fact, one of my colleagues used to refer to the M dwarf opportunity, that the small size of an M dwarf would allow it to have deeper eclipses. And that is absolutely true. So that is something that does work in our own galaxy. Although we haven't, it would be interesting. I haven't done this check. You can go, as you know, there are many planet discovery sites. The one I like is the one, I think it's called Exoplanet or exoplanets.eu. And you can ask yourself, you can even get graphs, you know, as a function of the mass of the donor star, how many planets are known. And I don't think that a very large fraction of the planets we've discovered are around M dwarfs. One of the reasons for that is that M dwarfs, being such small stars, are very dim. They can be thousands of times less luminous rather than our sun. And so we don't see them at great distances. These X-ray sources have the advantage of both, many of them, not all X-ray sources are bright either, but the X-ray binaries that we can see in other galaxies are very bright. And so they're bright and small, and you can resolve them. They're not crowded together because there really aren't very many of them in the galaxy. It's hundreds of billions of stars. There's only, a relative handful of these things. So it's that combination that made it work. But that was really an excellent question, because in fact, what you're doing is you're pointing out what Dave Charbonneau called the M-dwarf opportunity.
Yeah, that's interesting. I was amused by your nomenclature for the exoplanets.
Yes, right.
That's great. I mean, if you coined that term, we need to put you to work to name things like what Pluto is now.
Well, I think maybe one day Pluto will be a planet again. That's who knows? It could happen. It would be interesting to hear from your membership what they think about Pluto. Should Pluto be a planet or not? I would love to hear what you guys have to say about it.
Well, we've all been through the 4th grade a long time ago, so. All right, anybody else?
Don't forget to unmute yourself.
Dr. Di Stefano, I was just wondering, given that this is an analysis of existing databases, would the implementation of AI help accelerate the process?
Yes, indeed. In fact, what I spent most of today doing was writing a proposal to get some resources to do more work finding more of these in X-ray data. And it turned out that actually the discovery part of this was fairly straightforward. But there could be many things that we're missing. And so, yes, we would like to use the techniques of machine learning in looking for this, particularly because you'd ideally like to look at all of the light curves that have ever been taken. And so one of our collaborators is the person who is the curator of the entire Chandra archive. And he is an expert in machine learning. And he has run some of his codes to try to find anomalies. And by anomaly, we just mean something that's unusual. And of course, a planetary transit is unusual. This is the only one that's ever been found. So he actually did identify a group of objects that included this in his first try. So that's very promising. So yes, absolutely. AI is a good way to go. At another talk that I gave, people recommended something that I've also been thinking about, which is what about citizen science? What if we just put a bunch of these light curves up and let people look at them? The only thing about that is that if I share with you what's the hardest thing about this, it's the analysis, it's the modeling, right? And it's the skepticism that you have to have. If you go into this and you think that everything that you see that's a dip is a planet, you're going to be making a lot of bad mistakes. We're at the beginning of a new phase of discovery. We have to be very careful, right? We have to make sure that we've really done our best to give a skeptical look to all of this so that what we find can be described in a clear way. And as I said, we can't say for sure this is a planet, it's a candidate planet, but we wanted to really make sure that nobody jumped to any conclusions at this point. And the refereeing process was also helpful because they were very clear about the fact that this is an extraordinary claim and it needs extraordinary evidence. So we really had to work very hard at this latter part. So I would love to think of a way to involve the public in some of this analysis as well, because that would be very helpful.
Would it be possible to parse it out like the at-home SETI project did?
For a second. Well, we have to think about it. We need some creative ideas to figure out, as I said, for the light curves, I think the answer is yes. But there's so much more to it that we have to really think about what we can ask people to do. We'd like them to do things that really help to move us forward. Certainly the light curve studies do that. And the question is, should we just do that, or should we try to take it further with what we're asking the public to do? Because, some of the people out there are just phenomenal, right? They make, I don't know if you're familiar with from Zooniverse, in the early years, there was someone from the Netherlands called Hanny, and she actually discovered an object. It's called Hanny's object. And it's a kind of a green, interesting object that turns out to be a special type of galaxy, right? People can do wonderful things if you set them free with the data. So the question is, what do we set them free with? So both the AI and the citizen science, I think, are good ideas. And if any of you have ideas about that, just let me know.
Thank you.
At the risk of being a little off topic, one of last year's presenters was really famous for recruiting autistic people for pattern recognition in some of the light curves he was getting using space telescopes. So that turned out to be sort of an interesting solution to
that wasn't
pattern recognition.
Who is the person?
Kayvon Stassen.
Yes. I was just going to ask if that was him. Yes. He's remarkable. And certainly he's somebody to talk with about this. It's funny because I've talked to him a little bit about using some of the remarkable stuff he's done with tests for microlensing. But I had not thought of getting him involved in this. I just heard a talk by him fairly recently, though, and he was not talking at that point about getting autistic children involved in pattern recognition. Another thing that we've been thinking about is sonification. And there's something we didn't know when we wrote this paper. We're writing another paper now about the pattern of eclipses when you have something that's transiting a binary. There's more to it. You can have multiple transits in a relatively short period of time. And a great way to discover that would be with sonification, it turns out. It's maybe a little bit too much for me to explain right now, but that has something in common with using the talents of autistic children to look for patterns. Here you're looking for sound, and a lot of the impetus for this work comes from well, I'm not sure where all of the impetus comes from, but I know of one person who has been doing this and is a blind astronomer. And so she's been interested in sonification as a way for her to do her own research.
Yeah, fascinating.
Well, I have a question, but I think members should go ahead of me. So put me in the queue, Victor.
Put you in the queue for what?
For asking a question. I didn't think I should precede the members.
Oh, no, go.
Well, so I really love to talk, but I'm puzzled by one thing. So maybe you could straighten this out. When you think about the X-ray binaries, the X-ray beam, if you will, is in alignment with the axis of the accretion disk in your model, correct?
Well, when you say the axis, I guess the X-rays are coming from the central portion of the accretion disk.
In a direction that's more or less perpendicular to the plane of the accretion disk.
So you're saying if the disk is like this, it's like the jet? Not necessarily, no. That
Well, let me ask the rest of the question, because maybe it's a stupid question. What would you be surprised that the planet or the transiting object, the planet, is in a orbit whose ecliptic, if you will, is intersecting that vertical axis in the geometry that we're visualizing here in relation to the accretion disk? Like, why aren't the physics leading to an equilibrium where the planet or the object would be in orbit in a plane close to that of the accretion disk? That's what I'm struggling with. Does that make any sense?
It does make sense, but I think that the problem is that the visualization of having this be the accretion disk and this be the axis and the planet being like this. Well, we really don't know exactly how the planet is going around, but it's very likely going around, sort of in the plane of the accretion disk, more or less. Maybe not exactly, because otherwise the disk might block the X-ray source. Now, we don't know for sure, but your question actually makes a lot of sense, because if you ask yourself, what is the probability of seeing a transit? There are two parts of it. One of it is, what is the probability that this object has an orbit that is aligned with our line of sight? Okay. And that can be a very small probability. That can be, something that is, on the order of 1 in a million. But that's not the only part of it. The other part of it is that you can only see it at a certain point in its orbit. And we see it for a few hours in an orbit that may take 60 years. So that's also a very low probability. And you multiply these together, right? So what's the probability that we're seeing this planet? Well, honestly, we don't know, because we don't know what these orientations really are, right? What we do know is that we studied about 2,600 light curves from over 200 sources, and we found one. So if we just go by that, if we look at a large enough body of additional data, there's no reason to think that we wouldn't find more, because we didn't have a special way of selecting this data. We just took 3 well-studied galaxies and looked at those, right? So given that, that's the empirical approach, right? Well, we looked at this many light curves and we found one. Let's look at 10 times as many, and we should find additional ones, right? But the fundamental question of probability is very challenging in this case. Now, it turns out for this system, we also see evidence of eclipses by the donor star. So that means if we're seeing eclipses by the donor star, there's some probability that this planet candidate is coplanar. And when we look at circumbinary planets in our own galaxy, there's a tendency for coplanarity, right? Now, when you look at the probability calculations, which we did in the paper, if you have coplanarity, which is, I think, what you were suggesting, you were saying you were puzzled about having it the other way. And I think the reason is because the probability is higher if you would be able to enforce coplanarity.
But I guess I don't understand how coplanarity allows it to block the X-ray emission during the transit event. It seems like it's never in position to block.
Well, if you had a very thick disk and the disk blocked all of the X-rays, you're right. So you either have a thin disk or the disk is slightly inclined with respect to this orbit. So, getting into the geometry here is actually an important thing.
Thank you. Really interesting. Challenging.
Yeah. It's kind of fun to think about all of this stuff. Yeah.
Okay.
Hi,
any other-
Dr. Di Stefano. I have one question. This is Ashok Shah. Excellent talk. Thank you. Have you also observed in the data whether this object, let's call it the planet, also eclipsed the donor star?
Well, that's an interesting question. We cannot tell that. And the reason is several-fold. From a practical level, this donor star is, if it's emitting X-rays, it's at a very low level compared to the compact object. So we don't actually see evidence of the donor star at X-rays, right? So we can't see an X-ray eclipse of the donor star. But the other thing is that the donor star is very big compared to the planet. So I think it was James who earlier was talking about the little dip that you see. If you look up the transits that people have found where planets are discovered in our own galaxy, these are often very small dips, except maybe in the case of M dwarfs. So this dip is so small because the planet is small compared to the thing that it's blocking. It can only block a tiny portion of it. So this planet would not be capable of blocking a large enough portion of the donor star that we would be able to detect the change in the donor star's luminosity. But the donor star is not really an X-ray source anyway. So that's, a fundamental, and that's great, because if it were, we probably wouldn't be able to see what we do see, which is the blockage of this very tiny X-ray source by a very tiny object.
Thank you.
Does that answer your question?
Yes, it did. Thank you.
Okay, great.
I have a question. This is Dave.
Right.
Maybe I misheard you, but you said that because the planet, it takes 20 million years, it's not long enough for life to evolve.
Mhm.
So you're saying that the whole planetary solar system only lasts 20 million years?
Oh, not that it lasted 20 million years. It's just, suppose you go back in the history of our solar system and ask yourself, when was it possible for life to start, and for life to start evolving? Well, I'm not a biologist, and I'm not even an astrobiologist, so I can't really tell you that. But I do know that the time scale is generally much longer than 20 million years. So it's just a question of how long it takes for things to cool down, for the processes that might possibly lead to the development of life to take place. Those are thought to take much longer than several million years. I don't know whether we're talking about hundreds of millions of years or billions of years, but, we're not talking about this tiny amount of time that the system has lived. So every planetary system goes through a period where it's young, and young planetary systems probably don't have the right conditions for life. And the interesting thing is that even if they did, some of them would get sterilized. For example, an M dwarf, these very small stars that we're talking about, M dwarfs tend to have a lot of X-ray flares when they're young. And that goes on for something like hundreds of thousands of years. So if you had life on a planet orbiting a young M dwarf, it is thought that the M dwarf would sterilize the planet. So if there would be life there, that life probably would have started later.
But it would take longer than 20 million years for the planet itself to evolve, correct?
For the
I mean,
planet
Earth, for instance, I think it's 4.5 million or something like that, or 4 million around there. Or 4 billion, 4 billion.
Well, the sun, I guess, is about 5 billion years old, right?
Yeah.
And the Earth is, I really, this is not my area of expertise, so I don't want to start throwing around numbers that may not be exactly right. But, the Earth And then life on Earth, did take a while, for the planetary system to form. In fact, there's an excellent point associated with what you're saying. These stars in the Xray binary are very massive stars. They had to start out to be very massive in order for them to become either neutron stars or black holes, right? So we know that we have at least one compact object there today. So the star was very likely more massive than 10 solar masses, and it could have been significantly more massive than that. In our own galaxy, we have never found a planet around such a massive star. It's not because they don't exist. We don't know if they exist. We can't find them because these stars are so bright and so variable that it's hard to use the standard techniques to find planets around them. So the other special thing about the discovery is that this is the discovery of a planet around a massive star. And so it suggests if you have this object that has a well-defined surface in a system that is 20 million years old, that the process of forming it was able to complete in 20 million years. But we would not expect to find life there. At least according to my limited understanding.
I'm sorry. So it's not the life of the planet. It's just because it's so close to binary stars that it's unlikely that.
Yeah, well, it's also, it's the whole system, the planet is almost certainly something that formed with the system. If the system is 20 million years old, the planet is also young. It's not older than that.
Thank you.
Did that answer your question?
Yes. Yes.
Oh,
it
okay,
did.
great.
It's interesting that, there are a bunch of us who do, outreach, and we like to tell people, well, that's so far away that, it's not even that way anymore. It's not like that now. And it turns out that now is a pretty slippery word. And what you're talking about now is just giving us a whole new thing to wrap our heads around.
Right, because this is so far away, right?
The same now as it used to be.
Yeah. It's a fascinating thing, though. The whole, because you're looking at an extension of something that we knew. And, the other point I want to make is I don't think people would be surprised that there are planets in other galaxies. Most of us would be shocked if there weren't. Right? Because there's every indication that other galaxies have similarities to the situation we find around us in the Milky Way. And that therefore, if we have planets, they have planets. And we understand a little bit about the whole process of planet formation. Experts on it would say that we understand quite a bit about the process of planet formation. And there's no reason to think that this doesn't take place in other galaxies. So the thing that's really, new here is actually finding something that seems to be a planet in another galaxy. It's the discovery of it. The idea that these galaxies are similar to the Milky Way and that therefore they must have systems in them that are similar to what we have in the Milky Way. As I pointed out early on, that goes back to the mid-1700s, right?
All right, well, this has been so fascinating. We could do this for a while here, but I think maybe we should, unless anybody has any last questions, we should say goodnight. And thank you very much.
Oh, well, thank you for hosting me. I'm going to end the share so that I can really see the whole group. If I can I do that? Let's see. Yeah, there we go. And then I can get rid of, there we go.
Thank you.
So thank you very much for
Thank you,
coming
Roseanne.
tonight.
This has been delightful.
It was really a pleasure.
We loved it. Thanks so much for your energy and your thoughts and your fantastic discovery, and good luck in keeping it going. We'll keep an eye on the literature to see what's happening.
Well, that's great. We'll try to make there be more literature. Don't expect anything in the immediate future. Okay, take care, everybody, and thanks again.